So we're very fortunate to have Mustafa Amin here for the first lecture. Mustafa undertook his graduate studies at Stanford and received his PhD in 2008. I was actually a graduate student at the same time as Mustafa, just a few years younger, and I can say that as a young graduate student, I always looked up to Mustafa as a...
It was the other way around.
No. Always providing like really clear explanations for things, and I'm sure you'll really appreciate that in his talk today. So after his PhD, Mustafa moved on to a postdoc position at MIT with the prestigious Pappalardo Fellowship, and then he became a senior Copley Fellow at the University of Cambridge. At the moment, he is an assistant professor at Rice University. So Mustafa's research focuses on the earliest moments, the cosmological history, just right after the Big Bang. Tonight he's going to share his insights on the nature of dark matter and dark energy, some of the two most important components of our universe, and also the two most mysterious components as well. So I hope you enjoy, and I'll leave the rest to Mustafa.
Thanks a lot, Mary Angela. Right, so it's an absolute pleasure to be here. I've been here now 4 times before, and every time I've been here, I don't want to leave. I just want to stay behind. And it's a great pleasure to have this opportunity to actually tell you about some of this amazing stuff that our universe is throwing at us. So the title here is pretty cryptic. You see 2 quotation marks on there. So it's Seeing the Invisible. Seems quite contradictory. But hopefully, my goal is that through the talk, I'll tell you what I mean by this and how do we actually see the invisible in our universe. And please feel free to interrupt me throughout the talk, and I'm also here after the talk, so don't hold your questions to the end. I'm happy to take them as we move along. Okay, so I'm going to be talking about things that we can't see, but before that, I want to start with a bit of orientation, and this is an orientation of our position in space. So let me start with something that hopefully we can all agree upon. We are here, right? It's here in space, but a little bit, just a few minutes back in time. Okay? So we're all okay with this, that we are here. Yeah? But where is here? So our cosmic address has quite a few things we have to say about it. So we're here in this room inside the Aspen Center for Physics, which of course is in the beautiful state of Colorado, which is in the North American continent, on our blue planet Earth. Our planet is nothing but the 3rd rock from the sun in our solar system. And our solar system is but a tiny speck in this huge galaxy of ours, which has about 100 billion stars like our sun. Just to give you a sense of scale, this is right here in the room, it's about a few meters. This is 6,400 kilometers. This is much bigger than that. Okay? Light travels pretty fast, and on this scale, light would take about a few hours to get from Neptune to the sun. So we're on humongous scales as we go here. And the galactic scale is even more enormous. We are situated about 25,000 light years from the center of the galaxy. That means that it takes light about 25,000 years to get from the center to us. Okay? So that's the scale of these things. So that's good. So I've told you a little bit about where we are in our cosmos, okay, inside our galaxy. But that's not all. First of all, this galaxy, as you all know, our galaxy is like a flat pancake, and this is an artist's impression of what it would look like face on from the top. What does it look like from the Earth, and in particular from here in Aspen? It looks something like this. This is actually a picture taken a couple of years ago by my friend Andrei Frolov on Independence Pass at about 11 p.m. Okay. So this band that you see is the galaxy as we see it sitting inside the galaxy. Right? It's a pancake, so we are looking at it from the inside. And it doesn't look, in the sky, when you look at it, at least it fills me with awe when I look at this. But here it just seems like a band right here. Now, do I want you to focus on this galaxy? Not so much. I want you to focus actually on some region here which is completely devoid of stars. Okay? It's black. You can't see any stars at all. Okay? So this is our galaxy, but I want to go beyond. So this is a small region of the sky that I've picked up, which is completely black, and I can't see stars in it. What is the size of this region that I've picked? It is about this size compared to the size of the moon. So it's a pretty tiny region of the sky. Now, if you look at this region with the help of glasses like mine, which are pretty powerful, then you see this image. Of course, the glasses I'm referring to is a Hubble Space Telescope. Okay? So with the Hubble Space Telescope, you see an incredible image in this small region of the sky. And each of these blobs that you see, almost every one of them is a galaxy like our own, with about 100 billion stars. So each small region of the sky, and this is not atypical, every place you see, you will see a picture like this. And I don't know if the lights are too bright, but can you see a spirally structure? Okay, that's kind of like our galaxy. Of course, we can't see us. Again, another one here. There are different types of them. Can anybody spot the stars in here? There are some that are stars and not galaxies. Sorry?
Are they yellow?
No, there's another way.
There's a shift.
Do you see this one? Do you see these spiky patterns? Okay. So that's how you can tell that this is not a galaxy. In this image, this is a star. Okay. And this will come back. So if you remember this, we'll come back to this towards the end. Okay. Let's see.
There's a yellow one with spiky.
There's another one here. Yeah, right there. Okay. All right. So clearly, by this point, at least I feel humbled and insignificant at how small we are in terms of size and scale in our universe. We're sitting here on this third rock from the sun, and we're talking not only about our solar system or our galaxy, but now so many of these galaxies out there. And just to give you a sense of numbers, there are about 100 billion sun-like stars in our galaxy, and there are about 100 billion galaxies that we can see in the sky. Okay? That's a lot of stuff in our universe, and we're just a tiny speck in here. However, this is not the end of the story. Indeed, the amazing thing is that there is evidence for there being a lot more stuff than we can see in our universe. Many times more invisible stuff, because we can't see it, otherwise I would have shown pictures of it here. There's evidence for it in our universe. And it's invisible, essentially. So the question arises, if I'm saying there is stuff, or scientists are saying there is so much stuff, how do we know? How do we know there is more stuff than visible matter if we can't see it? And this is the main part of the talk that I want to get to give you an understanding, or explain what I understand of why we know there is so much stuff out there that we can't see. I'm going to lay out the case for this invisible stuff in 3 parts, based on how stuff moves, how images of things that we can see are distorted, and how things that we see in the sky, how they are being held together. Okay? Based on these 3 bits of evidence, I'm hopefully going to try to convince you there is a lot more invisible stuff out there than we can see. And the key player in all of this will be gravity. Okay? That's the thing that's going to help us figure out whether there is invisible stuff out there. All right, so let's start with the first bit of evidence. Again, something we're familiar with, right? The Earth is going around the sun at about 18.5 miles per second. We're about 93 million miles away from the sun. Said another way, it takes about light 8 minutes to get from the sun to us. So the sun is moving around at this speed, the Earth is moving around at this speed around the sun. Now, what if somehow the sun disappeared? What I mean by that is not the mass of the sun disappeared, but it stopped shining. We couldn't see it anymore. But from far away, somebody still saw this motion of the Earth, like this. Well, if they had been familiar with Newton's theory of gravitation, or they had discovered those laws, then they would be able to tell that, well, if the Earth is moving in this way, at this distance, at this speed, using Newton's laws, they would have been able to figure out there is something in the middle with a mass of about 10 to the power 30 kilograms, which is the mass of our sun. So even if the sun was not shining, you could look at the motion of the Earth around it and say there must be a mass in the center, because gravity tells us for it to move like this, this is the amount of mass that is needed. So in this way, this is the first example that even if the sun was not there, by looking at the motion of planets, you could figure out what mass there is in the center. Let me say a little bit more. What if you were to make the mass of the sun 4 times as big, keeping the distance the same? Then you would find that the speed at which the Earth would go around would double. Okay? So it goes as a square root, like this. So that's one bit of information. Again, this just comes from Newton's laws of gravity. Another thing you would also notice if you looked at the speeds at which planets are moving around, you would find that the speed decreases as you go away from the sun. So you have 2 things, and we can understand this from Newton's laws of gravity. So what does this have to do with invisible matter? So let me now go to a larger scale, the scale of the galaxy. So based on these bits of information that I gave you, that speed is faster if you have more mass, and also if you move away from the thing that's causing stuff to move, like the sun, then speed falls away with distance, you would be able to predict, based on Newton's laws, the speed at which stuff moves around in a galaxy. So on the vertical axis is the rotational speed, on the horizontal axis is distance from the center. Notice as you move away from the region where there is stuff that we can see, the speed falls. Okay? And that makes sense, just like we saw in the solar system, that it should fall like this. However, this is what we would have calculated based on Newton's laws. What is actually observed here is this. Okay? This is what we actually measure the speed to be. So notice that the speed that we calculated doesn't match the speed that we actually measure. Okay? These observations were first put forth by Vera Rubin in the 1970s and 80s. Okay? And at that time, it was not easily accepted. Okay? But now, in some sense, this is one of the most fundamental observations that change the way we look at the universe. So this is your first indication that something is amiss. If we apply Newton's laws of gravity based on the stuff we can see and calculate the speed at which things move, it doesn't match up. So how can we modify this? Well, we want more speed here. Anybody have an idea of what we could do? Add more mass. Okay. We saw previously that you can increase speed by adding more mass. So perhaps if we add more mass in this region, we can't see it, so it's invisible mass that we have to add. Okay? It will increase the speed and match it with observations. This seems great, but you might say, you're inventing all of this mass to solve this one observational problem that you have. I don't know if I trust this. Maybe you got this observation wrong. People have tried this with many, many different galaxies and even larger scales things that we see. And every time we do see this discrepancy. Okay? So we need some more stuff there to explain why the speeds are faster. Any other reason people can think why the speeds could be faster? I'm genuinely asking. Sorry?
Laws of gravity.
Laws of gravity could be wrong. Okay? That's another possibility. But as we'll go on in the talk, I'll explain that it seems hard to do that. Okay? The observations that we have, for example, from current gravitational waves that you might have heard about, and other things that I'll mention, they make it hard to change the laws of gravity consistently. Be consistent with what we see, for example, in the solar system, and then change it here. Okay? Or consistent with what we see in the universe on the larger scales, and be consistent with this. But we'll talk about this a little bit. Okay, so this is your first bit of evidence of the fact that we need more invisible matter in the universe because of the way stuff moves. So that's the first bit. Let's now go to image distortions. So we've all seen pictures like this when we eat, right? You just put a spoon inside water and the image gets distorted. There's no real break here, but the image is distorted. And we've seen this with lenses. When light goes through lenses, it distorts images. What's interesting is that gravity also has the ability to bend light. So imagine you have a large mass like our sun sitting somewhere, and you see light coming from a faraway star. If it passes close to it, because of this large mass, you will end up deflecting light a little bit. Okay? So it's a very small deflection for the sun, but it's still, there is a deflection. So just like the reason you saw this distortion was actually light was getting bent a bit when it traveled from air to glass to water, or vice versa. The same thing kind of happens when you are passing near a massive object. Light gets bent a little bit. As a result of which, the images that you see of faraway galaxies, if there's stuff in the middle, if there's a lot of mass in the middle, it could get distorted. Hopefully, so this is sort of a fisheye lens, you can see the distortion here. This is a picture of the Abell cluster. I hope if the lights are good, you can probably see some distortions here. Okay? So galaxies typically don't look like these arcs like this. Okay? They're spherical or pancake-like. Some of them are irregular, but rarely do they look like these arcs. Okay? More importantly, notice that there is a coherence to it in the sense that it's all around some region. Notice the arc here, 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 here. Right? It seems like it's going around in a pattern like this. Okay? So this is an indication that gravity of the stuff that's in the middle is distorting the light that's coming from behind. Okay? What does this have to do with invisible matter? So here is again sort of a geometry. Okay, so here's a distant galaxy. You are seeing it over here. There's stuff in the middle that is sort of bending the paths of light that is coming towards you and distorting the images over there. We understand our theory of gravity. In this case, you need Einstein's theory of general relativity. Based on that, we can predict the amount of distortion you should see. You know the stuff that you can see. You can predict how much distortion of these images there should be. And it turns out that the distortion is more than what you expect. So again, you're led to this conclusion that if you want more distortion, you want gravity in this region to be stronger, which means you need to put more stuff there to make it work. Again, we can't see this stuff, so it has to be invisible. Yes?
I'm unclear on how some object, some galaxy, many millions of light years away, you're ascertaining that there must be more mass because it's not actually what you should have seen, since no one has yet traveled there with a caliper and measured that. So
Yes.
how is it we can make the clear statement that it's not what we should have seen?
That's an excellent point, right? So we absolutely, the question is, I can't travel to see what the galaxy actually was, and then determine, oh, it's actually distorted when I see. If it was just for one galaxy, then yes, you would not know. But what we are doing is we are doing this with a large number of galaxies. It'd be extremely unusual that all of these galaxies somehow manage to have this particular pattern around. So remember these arcs that I was showing you.
So it's the ellipsoid pattern
That's right.
convincing you.
It's this, look at these arcs, right? Okay. If one galaxy, sure, you could say, well, it crashed into another galaxy and it's got distorted, right? But you notice the pattern as a whole. Okay? That's hard to explain. And similarly, these ideas can be extended. We've tested these things with smaller objects as well, like stars and supernovae. And we've seen multiple images of them, and we've seen how it looks. So we believe we understand how this works in this context. So you're absolutely right that a single galaxy would be hard, but seeing patterns like this is quite convincing to know that there should be more stuff there. Okay. So that was my second bit of evidence for you. First was how stuff moves, now based on distortions of images. Yes?
Based on the observations that you've made about the bending of light, what is the ratio between the observable mass and the mass that we calculate has to be there to produce the amount of bending that is observed?
So it has to be more than 5 times of the regular stuff. Okay, so it's a lot of stuff that you need in here. Yeah. Okay. And one thing based on this question is it consistent with the types of ratios that you need in other systems? Right? And the answer is yes. It turns out that you calculated many different systems or as a whole, and that turns out to be consistent, which is in fact what gives us more confidence that it's not just someone. I mean, it's not that they're identical, but they're consistent with each other. Okay. The next, I want to give you one more bit of evidence, okay, about holding things together. So we all know that if you have a hot cup of coffee, if it's really hot, it's going to evaporate. Okay? Gravity can't hold it in place either. Right? It's going to evaporate away. Now, what does this have to do with invisible matter again? Instead of talking about galaxies, now I'm talking about a cluster of galaxies. A cluster of galaxies is typically a collection of galaxies bound together by about, maybe it has about 100 to 1,000 galaxies in them. Okay? So they're all bound together. One of the first things when people tried to think of this invisible matter was Fred Zwicky. He looked at the motion of these galaxies and found that they were moving too fast. Another bit was that if you look at this in other wavelengths than visible, you see that there is a lot of hot gas there. This hot gas is emitting X-rays. Okay? It's at about 100 million Kelvin. Okay? That's how hot this gas is. So this is all this hot gas here, and you can see the galaxies and the visible stuff here. And you can ask, okay, there's this hot gas, this stuff is moving around. Can the amount of mass that we see, can this hold this gas in place? Is there enough gravity because of this mass that can pull this gas in place? Otherwise, it would have evaporated away. You make this calculation, and again, you find that there is not enough mass in the visible stuff or even in the hot gas to hold this all in place. It would have flown away. So this is, again, some evidence to show that you need more mass than what is visible to hold this in place. Again, assuming we understand the theory of gravity. So hopefully, these 3 bits of evidence at least are making you think that, okay, there could be something there. Indeed, there's a lot more things that I could point out. My colleague, Katie Mack, gave a talk at our workshop a few days ago and listed 13 of them, okay, bits of evidence for this. I've just listed a few. The patterns in light from the time that the first atoms were produced, the crashing of clusters of galaxies, distribution of matter in the cosmos, all of these things, to be consistent with what we see, require some form of invisible matter. Okay? And you can ask me more about this towards the end. So I've told you there's invisible matter. I haven't much told you how it's distributed in space throughout. Like what does it do? By the way, I'm getting some feedback. Can I lower this a little bit? Are you guys getting some feedback? No? Okay. It's in my ears, clearly. Okay. So the next thing I want to do is tell you a little bit about how this matter is distributed in our cosmos. Okay. And also why it is distributed that way. So this is a visualization from a computer simulation of how dark matter is distributed in our cosmos. Remember the clusters of galaxies with thousands of galaxies I'm talking about? Those are this scale right here. This is a much larger scale. You can't see dark matter, so this is just a visualization in terms of dark and light, right? It's just what darkness means, that it's more dense there. And these bright spots are just painted on, okay, to say that there are galaxies and clusters of galaxies. So a structure that you see here is, hopefully you can see that there are some nodes, right? And they're connected by filaments. And it's a very sort of sponge-like structure in the way it's distributed. Again, this already is many millions of light years across, so this is 100 million light years across. Okay, so it's really large-scale things. And here is how this structure forms. Okay, and I'm going to run this again in a moment. So let me start over. Okay, and this time, notice that initially it seems pretty uniform, right? Everywhere there seems to be an equal number of particles. Now I'm going to let this grow, and the only thing I'm allowing is that these particles that are there, they can talk to each other with the help of gravity. Okay? And the one thing we know about gravity is greedy. Right? If it has a little bit of stuff, it'll attract more stuff. Okay? So if there are tiny little fluctuations from one place to the other, those regions will get more and more dense. The regions that were less dense will vacate and go to the more dense regions.
Excuse me, what does Z represent?
Sorry, I should have said. So Z, in cosmologists use Z. It's a measure of redshift. It's called a redshift. What it means is redshift. In this context, you can think of it as a measure of the age of the universe. Okay? So when z gets, sorry.
I'm sorry, I'm not hearing you.
Ah.
Speaking quickly.
So the z here, in this context, you can see it as a measure of the age of the universe. So when z gets to 0, it's today. When z is very large, it is far back in the past. A more careful answer to this question is that if you have light emitted from some star, the universe is expanding, so the wavelength of the light gets stretched by the time it gets to us.
Redshift.
It's redshift. So it's a ratio of the wavelength of the light that's emitted to the light that we observe. Okay? So that's what the redshift means. But the earlier the light was emitted, that is earlier in the history of the universe it was emitted, the larger the redshift will be. So that's why it's a measure of the age of the universe.
Thank you.
Okay, so this is just the movie going on, and you see the clumping because of gravity. Okay? And do you see nodes forming and filaments forming here, which is what the picture I was showing before. Okay, so this is a computer simulation of that. Now, you might still ask, okay, I've just shown you a computer simulation with gravity. Can I give you a little bit more? It turns out there's a good analogy for this form of clustering that you see. So as I pointed out, there are nodes, there are filaments, and there are voids in the middle. Okay, so nodes connected by filaments and voids in the middle in the distribution of dark matter. There's another place that many of the people here might be familiar with, and it is in this context. So you've seen we all have seen mountain ranges, beautiful mountain ranges here. Notice that the highest peaks are typically connected by ridges in the middle. Okay? So the large peaks that form as mountains come up, they're connected by ridges, and of course there are valleys. Another way, this is similar to how structure forms. Okay? Another way of an analogy I can bring up is, imagine I have a sheet of cloth, okay, a bed sheet, say, and imagine that I take my fingers, pinch the cloth, and just try lifting it up a bit. Okay? That lifting it up, the peaks come up, the highest, those come up, but they're connected by a ridge. Okay? So it's a similar way in which, in the early universe, when there's some density of dark matter that is growing, okay, there's some dense clump here, some dense clump here, and it starts to accumulate more stuff, it certainly accumulates, but then it's joined in the middle by this filament-like structure. Okay? So that is why we get these filaments and voids and nodes in the structure of dark matter. Again, it's just gravity doing its job. Okay. So I've told you quite a bit about invisible matter, and as was mentioned by Maria Angela in the beginning, we've given this invisible matter a name. We call it dark matter. Again, it's just can't see it, so we'll call it dark. But it begs the question that we know about this dark matter mainly from gravitational observations, whether by how stuff moves or based on the distortion of light or holding things together. But all of this were based on gravity. Okay? And the fact that we don't see it and we haven't detected it also tells us that it doesn't interact very strongly with regular matter that you, I, and the stars and stuff is made up of. But we still want to know more. Okay? We want to know what is dark matter. By that I mean I want to know how it interacts with regular matter, for example. Is it a particle? Is it something new? What is it? Okay? And I want to tell you a little bit about how we will know more about this stuff. So one possibility is that this dark matter, this invisible, that makes up this invisible stuff, is made up of some newly undiscovered particle. Okay? So we haven't discovered this particle that makes it up. It doesn't interact with straight light. It might take us a lot of effort to produce it. And one possibility is to produce it at the Large Hadron Collider in CERN. Okay? You smash protons together, and you try to see what comes out. We have some hope that in strong interactions you might be able to produce one of these particles. We haven't detected one yet there. Okay? Another way of trying to detect them is to build large vats of stuff that are under highly controlled environments. One example is vats of liquid xenon. Okay? These could be as big as 1 ton big. Okay? And what you do is then you wait for this dark matter particle to come and interact with one of your atoms or nuclei. Okay? And it's under such well-controlled conditions that you might be able to determine whether something like that had come and hit you. You want to build a big tank because you know that even if these guys are passing through, they're not going to interact with anything much. So dark matter might be passing through us, but it barely interacts with anything. So you have to make large enough vats that occasionally one of them will interact. So far, again, unfortunately, we haven't had a confirmed signal here. What else could dark matter be? And this is a continuing effort. Okay. It's amazing that we know about its gravitational influence, but we know very little about what this actual particle is. It could even be tiny or even large black holes. Okay. Lots of black holes floating around. It doesn't interact much with light. It interacts a little bit. And the dark matter could be made up of this. Okay. We don't know for sure yet. It could also be an extremely light particle, much lighter than the electron. This seems paradoxical. We want to create something that has more influence than regular matter. Okay. So it seems paradoxical, right? That something that light can give you dark matter. But remember, what we need is we can compensate for the lightness of a particle by just having many of them. Okay. So you can have lots of these very light particles and few of these very heavy particles, and they would together, either one of them could still work as dark matter. And again, as was brought up before, maybe it's the theory of gravity that's wrong, but currently it seems unlikely. How will we know, how will we distinguish between these many candidates? It turns out that the way structure forms in these, especially on small scales, right? Scales perhaps in the scale of galaxies or even smaller, the way structure forms in the universe depends somewhat on the nature of the dark matter. So these are 3 different candidates where we have done numerical simulations to see how the structure is different. In fact, this is very new. This is work still undergoing right now. This is work in progress. So you could look at the details of how structure forms in the universe and perhaps distinguish the nature of dark matter. There's another thing which I have somewhat hidden from you, which is that dark matter is not necessarily entirely dark. In some ideas that we have about dark matter, in fact many ideas, dark matter, when it finds another dark matter particle, it can annihilate, okay, and give off photons or some other forms of particles. And we can try to detect that. But I've told you that it interacts very weakly with everything and including itself. It's not very strong. So you need to go in regions where it's extremely dense to look for these signatures. One of the places where it's extremely dense is towards the center of our galaxy. So we look there and try to see if we see some excess radiation coming from there that could be from the annihilation of dark matter. Okay? So in many models of the dark matter and its antiparticle are both there, and they smash into each other. If they smash into each other, they give off light. Okay? So that's another way in which we are looking for it. And unfortunately, in some ways we see some signal from the galactic center, but there's so much other stuff there as well that it's not completely clear that it's really from dark matter, or is it from some other things, some other exotic, but things that we think we understand, like neutron stars and so on, emitting light there. So it's unknown. So we still don't have a confirmed detection of dark matter. But these are all areas that are currently people are actively pursuing to try to see if we can figure out the nature of dark matter. Okay, so we're at the point where I've told you that we, stars, gas, everything only makes up a very small fraction of the sliver of the universe. I've told you about dark matter. Okay? And remember I told you it's about 5 times regular matter. But notice there's a big part of the pie that's still left. Okay? So this was some invisible stuff that I told you about, which we call dark matter. But it turns out that observations are telling us that distinct from dark matter, there is something else in the universe, okay, about 70. And those were old numbers. I'm updating with new ones. About 68.3% of the universe is made up of something else called dark energy. Okay? So I want to tell you a little bit about this in the 15 minutes or so that I have. So we've learned about dark matter. What is this dark energy now? Is it just dark E equals mc squared? It's not. Okay? It behaves completely differently. So from dark matter. So how do we know about its presence? So this time we're going to go look at the universe on very large scales again and think about the question of what are distant galaxies doing? Are they just sitting there? Are they moving apart from each other? And how are they moving apart? So in the 1920s and early 1930s, astronomers, along with Edwin Hubble, noticed that distant galaxies were moving away from us. And they were not only moving away from us, they were moving away from us in a very particular way. The farther they were, the faster they were moving away. So this, along with the previous ideas put forth by Einstein's theory of general relativity, combined with that, it was somewhat evident that this could be interpreted as expansion of space. So space between galaxies was changing. So if you sit on any galaxy, you're just seeing everything else move away from you. And if it's stretching, the farther you are, it seems like the faster it is moving away. Okay? So he notices, and this has been known for a long time. Okay? So the space is stretching. For a long time, we think that another way of saying this is the universe is expanding. Yes, please. Did you have a question? Sorry. Okay. However, what happened, so this was known in the 1930s, but in 1998, there was a big surprise. Okay? And this huge surprise was that not only was space expanding, that the separation between galaxies was changing with time and increasing, but the speed at which they were separating was also increasing with time. So expansion of space was accelerating. Okay? And this was not expected. Okay? Why was this not expected? Well, because we had known from Einstein's theory of gravity that the way space expands is very much linked to its contents. Okay? So what is there in the universe determines how the universe is going to expand. It turns out that if you just take regular matter, and even things like dark matter that I've just introduced to you, stuff that clumps and behaves in the same way as regular matter as far as gravity is concerned, all of those things should have ended up slowing down expansion. So it's not so different from me saying that, look, we have gravity here. I throw this up. You notice that as it went up, it slowed down. It stopped. Right? So it was slowing down as it was going up again. Right? So normal gravity with normal stuff, what it tends to do is tends to slow things down, okay, as they're moving out. Gravity is greedy. It doesn't want things to go away. However, here we are seeing something completely different. We are seeing that the expansion of space is accelerating. It turns out that we need some really odd stuff, and it seems weird even to write this here, okay? Stuff which has negative pressure. Now, this is not an easy analogy that I can make for why gravity, stuff with negative pressure, allows you to give you accelerated expansion. But if you look through Einstein's theory, this is what you need. Okay? And amazingly, there is some ideas out there that behave in this way. Okay? But in general, stuff with negative pressure that causes accelerated expansion of space, that is what we give the name dark energy. What kind of stuff could provide you with such a pressure? Qualitatively, the energy density or the energy associated with nothingness, the energy of the vacuum, qualitatively has this feature. Okay? Another way of putting this is to say that this kind of energy density is different from regular stuff, because if you take a box of space and measure the energy density in it, now you say you expand the box. Naively, if you had some rocks or balls in it, the density goes down as you expand. This type of energy density is different because it's the energy density associated with space itself, that the density remains constant as you increase the size of the box. Okay? So this kind of energy density of vacuum has this property. The numbers don't match up, or we don't know how to calculate it, is one way of saying it. Okay? So we don't quite know what it is. Qualitatively, we have some ideas, but it's a mystery. Okay? We don't know what this stuff is. We know what properties it should have, but what really it is, how it fits in with the rest of the stuff we don't know yet. So just to sort of connect the two parts that I've talked about so far, We talked about dark matter, which was mainly responsible for the clumpiness of the universe. Now we have dark energy that is responsible for the accelerated expansion of space that we see. And both of these things we can't see directly with light. We infer its existence based on how stuff moves and things like that. By the way, the observations, if you are interested in how we knew about the accelerated expansion, we can talk about that as well later. Right. So at this point in the talk, I also start feeling uncomfortable by saying I've just told you about things we don't know. So much stuff that is unknown. So I want to bring us back to saying, how do we know that so much is unknown, and what do we actually know with confidence? So stuff we know in cosmology and physics for sure, with quite strong certainty, is that the universe started out pretty hot, pretty smooth. Okay? It has been expanding. Today, the universe is much colder than it was in the past. It is also much lumpier than it was in the past. Okay? So these are things that are pretty much, and this right here at the early time, the fact that the universe was hot and smooth is what typically we would think of as the hot Big Bang. In detail, we also know what has happened at different stages in the history of our universe. Okay? From the earliest fractions of a second, from the times to the time when the first nuclei formed, the first atoms formed, all the way to today, we have a reasonable idea of how these processes took place. By applying the physics knowledge that we have been able to predict, okay, this is how things should happen. For example, we can predict things like the ratio of hydrogen to helium that should be there in the universe at large. And it turns out to match. We also have observations now that match the data exceptionally well. So I haven't gone into any detail here, but this is a map. If you look out into the sky, and if you could wear glasses that only saw in the microwave, you would see that you're bathed in light from all directions, coming to you at a temperature about 3 Kelvin. Okay? So it's coming to you from all directions. If you take out that average value and look at just the deviations from the average, in false color you would see this splotchy image. So this is just like the sky wrapped around. The deviations are very small. However, they contain a wealth of information. So if you take this image of temperature fluctuation from the time the first atoms formed, this is where the light is coming from, and for the engineers here, if you take a Fourier transform of that, it would look something like this. It's a Fourier transform of this image would look something like this. Okay? It's a measure of how much power there is on a given on a given scale. The data points you can see right here. The theoretical curve is also shown here. Okay? The theoretical curve only fits the data if you put in the physics that we know along with the dark matter and dark energy that I've told you about. Okay? And then the fit is exceptionally good. So this tells us that we understand the properties of these things and the rest of the physics well enough that these kinds of matches are possible. Another fun thing to see is I have 2 images here. Okay. One is a simulation and one is from observations. Okay, of the universe. Can anybody see which one is a simulation and which one is an observation? So one is an observation of the sky. Okay? Anybody want to take a guess? Yes? This is what? Which one?
The observation.
Why do you think so?
There's a star.
Excellent. We come back to where we started. Right? And so you can see the patterns here in the stars, right? The simulations, they don't have them. Okay? But it's hard, right? It's hard to tell. So we've taken the physics that we know along with the physics of dark matter and dark energy, evolved the universe forward, and we can reproduce, at least qualitatively, the same features. Okay. All right. So, hopefully I have told you a little bit about our dark cosmos, and I've also convinced you that we can indeed infer the invisible from observations. And that inference has led us to saying that there is about 26.7%, again, these of dark matter, and about 68% or so of dark energy. And the stuff that you and I are made up of is a small fraction. And this seems relatively robust in terms of observations. So where next with this? To me, at least, this is quite an exciting time. Okay? So we have a pretty good model of, or paradigm of the universe that seems to work really well. The observations that we know are consistent with having a certain amount of dark energy and a certain amount of dark matter along with the known physics. Okay? However, it's clear that we're not done. We still don't know what the nature of dark matter and dark energy truly is. And something that I'm also interested in is how is the dark matter that we see today, how is it connected to what happened in the very early universe? Okay? How was it produced? How is that connected to the properties that we have today? And again, to me, the success of a theory is not just that it explains the observations that that theory was invented to satisfy, but also how it fits in with everything else that we know so far. So how does it fit in with the rest of the physics that we know? This is still something that's incomplete in the context of dark matter and dark energy. Right, so with that, thank you. Yes.
Are there a significant number of well-informed astrophysicists who contend that there is no dark matter, no dark energy, and what do they say about that?
So there is a fraction of people who think there is no dark matter, but typically you have to modify Newton's laws of gravity or Einstein's laws of gravity. And if you modify them in some region, for example, remember I showed you the rotation curves of galaxies. That you can do, but it's then very hard to fit other things like how dark matter behaves in clusters of galaxies. So there is a fraction of people who claim that it can be done. I don't know if I have seen something that fits all the observations that we know. Okay? And similar things are true for dark energy as well. It fits one observation where we need dark matter or another, but not the entire slew of things that we have. So is it worth pursuing? People still do, and I think people should, but I wouldn't say it's the majority of astronomers and cosmologists that think that way. Yes?
Frequently when physicists go looking for new particles, they have an idea of what they're looking for from the standard model, if nothing else. Yet the standard model seems to say nothing about dark matter. And it looks like the standard model has maybe missed 96% of the universe. What's going on in theoretical physics to look for hints at where we might look for dark matter?
So I think this is an excellent question. So a few years ago, there was sort of, not everyone, but a large fraction of the community, you could make estimates, just like you said, based on where could new physics arise. Right? What kind of particle do you expect beyond the standard model? And people had made predictions, and this was called the weakly interactive massive particle, the WIMP. Okay? And in certain regimes, we had some expectations that this is the type of particle we should see. Okay? Experiments have not revealed the existence of them. There's still a range of space left over. Okay? So we have guidance from theory to an extent of where to look for. But I think it's safe to say that the simplest thing we had expected did not pan out. Okay? So the ideas we have currently for dark matter, let me give you something that's of interest to me as well. So there is a problem in strong physics related to the strong force, okay, that found a solution in inventing a new hypothetical particle. Okay? This was there without thinking about it being dark matter at that time. It was invented for that purpose of solving that problem that was in the strong force. And it turned out that when people analyzed the properties of this particle that was needed, it turned out to satisfy all the things we need for dark matter. Okay? So this is called an axion. Okay? And this is also something that people have been looking for a long time. Unfortunately, we haven't found it, but it's also quite difficult to look for this particle. So that's another example of a kind of dark matter particle which was not invented to solve the problem, but turns out to have a bearing on this issue. Currently at the workshop we are at, there have been many, many ideas that have been suggested of what it could be. And the more interesting thing about them is those ideas, and I think what gets me interested in them as well, is along with solving these problems, they also predict new observables, right? Like saying, oh, you should see this much annihilation in these galaxies and so on. So there's a lot of I wouldn't say there's not a dearth of ideas in terms of candidates for dark matter. It's just a matter of we need to figure out better observational ways. We need to improve the observations so you can kill out swaths of these things.
Thank you.
Sorry, you had a question at the back.
You commented and then quickly passed over this. I can't help wondering, you see this in statistics all the time, that you're modeling something by virtue of what you observe, and therefore you do confirmational studies or confirmational experiments, and it fits exactly what you observe. But that's not at all surprising because you suggested the underlying theory and structure that you then modeled and came up with the answer that satisfied you. I just can't help but wondering, you see this the same thing if you go retroactively and look into statistics to pull out other variables that weren't powered to see it, but you come up with your own substrate of a thought process. You go, oh, yes, that's absolutely significant here, but it really wasn't because
No, that's
you comment on that, but you quickly went by and.
No, that's a good question, right? So the question of confirmation bias is certainly a good one. But I think the way I would answer this is that let's imagine to solve a problem, say I'll go back to this galaxy rotation curves. I said, okay, I need dark matter to solve this. There was no reason for the amount and type of dark matter, type of new stuff that I put in there, that it should have matched with what I see, say on the scale of galaxy clusters or in the light from the time of the first atoms. There was no reason that those even if I put in the same type of stuff, the amount of stuff, why did it turn out that it's consistent with all of them? Right? I didn't say if I measure the...
Because your underlying theory that you drew from to extract those calculations were incorrect.
No, but
but
the observations don't care, right, about my theory. The observations tell me there's this much stuff there, right?
Well,
But they both
based
turned out
on
to be
massive
consistent.
volume.
But both turned out to be consistent with each other. If they were not consistent with each other, then you would say, then clearly we would give up on this. The fact that they repeat independent observations of independent systems, given the model give us consistent answers, seems to indicate that the model is capable of explaining all of these phenomena. And in some sense, in science, I mean, this is what we do, right? We build paradigms and try to push our models to explain all possible observations we can get to. So up to this point, it's consistent with them. If tomorrow we find that some observation doesn't agree with this, you give up. Or you say, okay, your understanding was wrong about this, and you come up with a new idea. So up to this point, right now, all the observations seem to be consistent with this. Can I go? Yes, please.
How might the Webb telescope
Yeah. Yes.
shine some light on?
Good question. So the Webb telescope is going to be incredible. It's going to be a success. The James Webb telescope is going to be the successor to the Hubble, the beautiful images of what you have seen here. It will be able to peer into what is happening when the earliest stars and galaxies are coming into being. Those are also to an extent connected in terms of the nature of dark matter there is, because dark matter sort of creates the environment in which these first stars and things are forming. To some extent, and the way the universe is expanding at that time as well. So that will shed information on some of the things that I've mentioned here. So it would be good to have, and hopefully it will launch in 2021. Yes?
Can you draw a chart that shows distance on a vertical scale in logarithmic terms
Yes.
from the observation point and the rate of velocity at that point, 10 light years, 100 light years, 10,000 light years, the acceleration, is it smooth? And secondly, at what percentage, as far out as you can go into the universe, what percentage of the speed of light, c, are you seeing at the very, very extremities of the cosmos?
So I think we can find, if you interpret the expansion of the universe as just a speed, right, the speed at which it is moving, and I'll tell you this is not the right thing to do in a moment, if you take the expansion of space and you say that as space is expanding, a point here is moving away from me with this speed, which I would say is not the correct interpretation. you should think about it as space expanding, you will find that beyond a certain distance, and I can tell you the distance as well, the speed can exceed the speed of light. Okay? There's no problem with this, because just think about it. I told you before that what Hubble observed is the nearby objects are moving with some speed, but the speed was proportional to distance. You go far enough away, you can exceed the speed of light. Okay? But this has no problem with this idea of special relativity from Einstein, because it tells us about how stuff moves relative to each other. If you were standing at the location of the galaxy, you would not see it move past you at the speed faster than the speed of light. It is only because we are trying to sort of infer this expansion of space as velocity that this comes about. Maybe another example I can give you is just take an elastic band, put dots on it, and try and stretch it. Focus on one point in the center and see how fast the other stuff is moving. Okay? As you are stretching it, you will find the farther it is, it seems like it's moving faster. But stand at the location of that dot that you've put, and you see nothing moving past you. So to answer your question, maybe that's what you're referring to. There's no problem with with expansion of space, looking as if the speed of light or the expansion is violating the speed of light. Does that?
It's okay, thank you. No,
Sorry. Okay.
What? It's me, not you, believe me.
So okay, I'm sorry if I didn't.
It's okay.
Okay. Yes.
Earlier, when you were talking about the collider,
Yeah.
what's the science and logic behind colliding particles to emulate dark matter?
So what we are trying to do is, the question was, if I understood correctly, how is the collider going to help us learn something about dark matter? So the idea essentially is that when you crash these things together, when protons together, remember from Einstein's theory, we know that we can convert the energy that you put into mass and vice versa. Okay? So you can take these highly energetic particles, crash them together, and there is a chance that you will produce dark matter particles there. In the early universe, this could also have taken place. Right? Dark matter particles could have smashed into each other and given us regular matter and back and forth, as long as there was sufficient number of them and sufficient number of these collisions happening. So in some sense, we are trying to repeat that with the help of these colliders, okay? To produce some dark matter particles out of the collision of protons, essentially.
How do you observe it?
For example, we would see it as, remember, we can then track all the particles that come out, okay, of this crash. If we see some missing energy or some missing momentum, okay, then we infer, accounting for stuff that is not captured, that we know should have missing energy. Say neutrinos could also escape from that. Then you would say that, okay, for example, you've seen a dark matter particle there. Right? So missing energy would be one way of looking at it. Yes.
Several years ago, we thought the Higgs boson was dark matter and would prove dark matter. What about the Higgs boson didn't make it dark matter? And why does the existence of a particle prove dark matter?
So maybe I'm not familiar, but I don't think, at least I haven't been aware of thinking of the Higgs as a dark matter particle itself. It's hard for the Higgs itself to be dark matter, but maybe I'm not aware of all ideas out there. The existence of a particle, I think it proves dark matter in the sense that we know more of it. If we find this particle, we know more about it than just its gravitational influence. We've produced this particle with standard things, right, with protons and so on. So we now know something about how this dark matter particle interacts with regular stuff. Right? The fact that you were able to produce it means it had to interact with regular stuff to produce it in the first place.
How did you know it was what dark matter particle?
So the reason we're just searching for something that is like dark matter, which doesn't interact much with anything else, and it's, say, leaves a signature in the detector that is missing energy. And you're absolutely right to know that it's not easy to say that just because you saw missing energy, that particle must be the dark matter. What you then look at is, okay, what was the rate at which these interacted to produce the dark matter? And then say, okay, if this was also happening in the early universe, would you produce the amount of dark matter that we see today? Okay? So combination of those two things then can give you some confidence that, okay, perhaps the new particle that we observed there was the dark matter particle. Just by looking at some missing energy, it's not enough. So it's a very valid point there. Yes?
Something I hadn't heard of until I got in here this afternoon, when you're saying that some of speed of light, do you need to throw out your E equals mc square equation to be able to solve your problem?
So again, I think perhaps I didn't explain this well. So nothing is actually moving faster than the speed of light. If you stood at the location of where these galaxies were, you wouldn't see these galaxies zipping past you. It's just because we have an expanding universe. As the universe is expanding, the farther things are, they seem to be receding away from us at the speed faster than the speed of light.
So your limit is still the speed.
Is speed of light is still it's
because you're not dealing with light anymore. So if you're dealing with dark matter and dark energy and there is no light, could there be a second equation?
no, but it's the inference of dark matter and dark energy that we have relies on Einstein's theory of general relativity. So within it, it's built the fact that the limit of the speed of light being violated. It's just within the theory, it's not possible, and there's no observations that indicate that that's being violated either. Yes.
So when you talk about space expanding, you're talking about the dynamics of this thing we think of as space. I've heard it pointed out that when you look through a telescope at some distant object, you can think of it as looking back in time. So is there a way to talk about the dynamics of time in the same way that you've been talking about the dynamics of space?
To an extent, yes. Time and space within Einstein's general theory of relativity are linked together, but they're also somewhat different. So if you're thinking about, I can think about stretching of space, and you might also have heard about bending of space right around us. So you can also think of bending of time in a similar context. For example, what is bending of space but saying that, if you put in a flat ruler there, you would find that, if space is bent, I have to put more flat rulers to actually cover that same region. In the same way, time also has a bending to it, in the following way. If you think of how your clocks run on the surface of the Earth compared to how they run far away from the Earth, which is linked to the fact that space and time both are bent around the Earth, you will find that they are run at different rates. Okay? So in that sense, you can certainly think of time also having similar properties as space, and it also having a dynamics. That is, how you measure the ticks will depend on what the curvature of space and time both are doing there.
Do cosmologists talk about the dynamics of time at all, or do they just talk about the dynamics?
No, you talk about both. You think of both time and space together. Right? So it's usual to think of using time as a sort of way of keeping track of things, how they evolve. But I could have used a different type of time and it would have completely been okay as well. And you could have then, instead of thinking, I shouldn't think of time as something that's keeping measure, but thinking of this whole space and time together and looking at the dynamics of it together, and that would be perfectly fine as well. It's just that because of our usual way of thinking that time, we think of evolution in terms of time. That is our way. That it's normal to write down equations like that in that way as well. This is true, again, I shouldn't say that time is completely the same. There are still differences. For example, when we write laws of quantum mechanics and things like that, you definitely need a time to keep track of things. Okay? So it's not completely the same, but there is no problem in thinking of space and time together as a dynamical quantity. Okay. Thank you very much, and we're ending.